Let's just now take a moment and look at just a quick review of integration, which is kind of anti-differentiation, right? Thanks to the fundamental theorem of calculus. So let's just take a look at a few integrals to remind yourself of some of the things. And again, if you need to review further on this, you can dig a little deeper. But let's look at this one. Let's look at the integral of x cubed dx. Now this one, the integral here, we're going to use the simple power rule. This expression or terms like it or polynomials made of terms like this, these are the easiest to integrate. They're just going to be x to the fourth over 4 plus c. All right? Just the power rule. And so the power rule, if we remember, is simply that the integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. All right. Now, moving on to just some other common ones that we're going to run into. Here's an interesting one that looks like it might be a mistake, but x cubed dy. We do this. This is kind of important that we pay attention to what we're integrating with respect to, right? This is not something we get into a lot in first semester calculus or even second semester calculus, but the dy tells you what to treat as variables. And so in this case, it's saying y is a variable. Y is your variable of integration. Anything else you just treat as a constant. So we would treat the x cubed as just a constant term. And so the integral here would just be x cubed y plus c. Just to help you, if I just came along and asked you to integrate, say, 5 dx, I'm asking you to integrate the constant term 5 with respect to x. And so the integral would be 5x plus c. So that's the same thing that's happening here. We're treating x cubed just as if it were a constant, because we're integrating with respect to y. So just something to be aware of. We do start to pay attention to those dx's and dy's in this class. Of course, let's look at some. We will integrate e to the x, which of course is just itself, because we're trying to find the function that has the derivative of e to the x. And we know that the derivative of e to the x is e to the x. All right? E to the 3x is just going to be a copy of itself. But you need a 1/3 factor there to counteract or to account for that 3x in the exponent. Integral of natural log of x dx is... Now this one represents, it looks like it should be simple. So the question is, can you find a function that has the derivative of natural log of x? And the one mistake you don't want to make is to say, oh, that's just 1 over x. That's actually wrong, right? The derivative of 1 over x is not natural log of x. The derivative of natural log of x is 1 over x. So this represents in order to integrate this, we have to use parts. So integration by parts, you take your integral and you classify part of it as u and the other part of it as dv. All right. So like for instance, in this case, we'll let u equal natural log of x. That means dv is everything else. So in this case, just dx. And integration by parts says that the integral of anything u dv is equal to uv minus the integral of v du. Okay. This integrating by parts gives us the ability to integrate things that are more complicated. So again, everything is determined by what you choose to be u as. So u is ln of x, dv is everything else. And so if we follow through, that means du is 1 over x, and v is x, because you take the antiderivative of dx to get v. And so if we plug it into our little formula here, this will equal uv, which is ln of x times x. Of course, I would normally write that as x ln of x, but we'll put it like that just to keep it consistent, minus the integral of v times du. Du is 1 over x dx. I guess I forgot to put the dx down here. Okay, but look what happens. That x times 1 over x cancels out, and you're just left with dx. So if I just I'm left with x ln of x minus the integral of dx, which is just x plus c. So that's a much more complicated antiderivative. The integral of natural log is this right here, and I don't recommend actually memorizing this. What I recommend is remembering how to get it by integrating by parts, and that's how you find that integral. So integrating by parts is an important tool that we want to make sure we remember, right? So here's another example of integrating by parts. So integral of x squared e to the x dx. So again, what we do is we choose part to be u, and the rest will be dx or dv. In general, if you can, choose a polynomial term or a power term for u. That way du is just real easy to find, just 2x dx. Dv will then be, of course, the rest, e to the x dx. And the big thing is, whatever we choose for dv, we need to be able to find its antiderivative easily. And yes, the antiderivative of e to the x is e to the x. So it's going to be uv. So x squared e to the x minus the integral of v du, all right, v du, right? And so v du is e to the x. Let's put it here. V du is 2x dx. Okay, which I can bring that 2 out. But notice I've got to be able to integrate that right there to find this ultimate solution. So that's got to be, I've got to be able to evaluate it. And again, it's not something I can just evaluate using simple rules. So how do I do it? Looks like I'm going to need to use parts again. Okay, so let's choose again. Let's choose a u, and we're gonna bring the 2 out there, so we don't even have to mess with it. So it's going to be, u will be again just x. That means dv will be the rest, e to the x dx. Du is equal to 1 dx, or just dx, and v is equal to e to the x. So here's what I've got. Let's see if I can. This thing now becomes this right here. X squared e to the x minus 2 times this integration by parts, v du. So, uv, so x e to the x minus the integral of v du, so e to the x dx. And look, now I can integrate that. So we got x squared e to the x minus, we'll distribute that 2 through there. So it becomes a plus 2. The antiderivative of e to the x is just e to the x, and then we have plus c. Now I'll mention this. We can factor in e to the x out of everything, leaving an x squared minus 2x plus 2 plus c, right? So those are some reminders of some of the integration that we need to be able to do. Now, you also may want to take a look at integration using partial fraction decomposition, because we do need to be able to integrate. And of course, all of the tools that we learned in calculus, we need to have at hand. So we just basically covered a little bit of integration by parts, but there's integration by substitution, and there's also integration using partial derivatives. And of course you get things like trig integration and things like that. So yeah, there's a lot of calculus you want to just remember. Now don't panic. If you don't remember it all, we'll kind of build it in as we go along. But this gives you some things to start with.